Okay, so we are going to begin with the topic of 7.3, which is the structure of matter. So the structure of matter. Now if you remember, we had Rutherford and his gold foil experiment. In this experiment, the alpha particles were made to approach the gold foil. And if you remember that from this experiment that we had here, where we had the gold foil having your proton and neutrons, and then you had the alpha particles which came right straight and then bent back. There were some which bent in the other directions, some bent in the other directions, and there were also many which simply passed through the atom, right? Okay, through the atom. So many passed through the atom. Because of this, they concluded that atom is mostly empty. Atom is mostly empty. Now the whole focus went into the nucleus, which had your protons and neutrons. Now people started developing the curiosity further, and there were discovery of new particles. So this experiment led to further research and many new subatomic particles were invented or discovered. This is what exactly led to the birth of particle physics. So particle physics explains the fundamental nature and of course this experiment, if you remember, was done on the Geiger-Marsden. It's also known as Geiger-Marsden experiment. So let us now begin with particle physics. So what is exactly this particle physics? To understand this, we have to move little down. So I will just go little down. Okay, and we will begin understanding this particle physics itself. Particle physics here will deal with fundamental particles. Fundamental particles. There are three fundamental particles. Okay, so the first fundamental particle are leptons, and electrons come under this category. Second is quarks, and our proton, neutron come under this category. And the third that they found was exchange particles. Let us begin with one by one now. So to begin with, let us understand first what are leptons. Okay, what are leptons? So these are particles. These are particles to which electrons belong, and also the tau and muon belong. So there are three particles. Because there are three particles, so there are also three antiparticle, which means if there is an electron, then there is also positron. So electron is shown as a particle E, then this is the antiparticle which is shown as this. So this is antiparticle, whereas this is particle. Then you have your tau and anti-tau. Then you have your muon and anti-muon. Now, charge of all these particles, you have to remember that the charge of electron is -1, whereas charge of the antiparticles are +1. So it is -1 + 1, -1 + 1. So this is the category of charge here. Okay. You should also know something which is called your Lepton number. For all the particles, the Lepton number is always +1. For antiparticle, Lepton number is -1. So particle +1 and minus 1, plus 1 and minus 1, because antiparticle here. So this is your lepton number. Now there are also some other particles. There are also other particles like neutrino, and antineutrino and antineutrino. Each of lepton has a associated neutrino particle. For example, electron E has neutrino particle as mu E, and antineutrino is E. Now, what does the symbol mean? This means belongs to electron family, released along with beta plus or beta minus. Similarly, for tau, we will have mu tau and antineutrino of tau, like that. Okay. Now this is about leptons. So what are leptons? Leptons are that category where the electrons belong. Okay, so it is a category where the electrons belong, and it also has other members in the same family along with electron. They are tau and muon. Now each one of them have some associated particle which are called your neutrino particle. So for example, your electron will have a neutrino particle which is known as this nu E. So for anti-particle, that is positron, will have the same nu E but with a dash here at the top. You can see here. Okay, so this is about leptons. Now let us go ahead with quarks. Then what are quarks? Let us understand. Now quarks, there are 6 type of quarks. Quarks, which are known as your up, down, then top, bottom, then strange, and charm. Now these two are very important. Why? Because protons and neutrons are made up of three quarks of up and down combination. So how do we know whether it is up or down? You have to know this from a chart which shows that the up CT, they have a charge of plus 2 by 3e, and the down, strange and bottom, they have charge of minus 1 by 3e. Okay, so which also means that your antiparticle of up, charm and top, they have charge of minus 2 by 3e, and antiparticle of down, strange and bottom have charge of plus 1 by 3e. I think this is very important for us. Okay, let us say, for example, now we will apply an example here. If I take proton, how do we write? Let us say we write 1 1. So which means charge is plus 1. So what combination will help in getting a proton? Okay, so let's see now. I can make plus 2 by 3e plus 2 by 3e and minus 1 by 3e. That will give me plus 3 by 3e. That will give me plus 1e or plus 1. This e value is 1.6 into 10 power minus 19 coulomb. This shows what? This shows that the proton should be written as up, up and 1 down. Okay, so similarly you can now make for neutron. Similarly, neutron. So for neutron, if you make, what are you going to make for neutron now? Charge is 0. Is 0. So if I do plus 2 by 3e, then I have to do minus 1 by 3e minus 1 by 3e, which means up, down, down combination. Okay. Next. These quarks that you see are combination of 2 or 3 and are known as mesons for 2 quark combination and baryons for 3 quark combination. This is very important for us. So mesons for 2 quark and baryons for 3 quark. You should know this. Both mesons and baryons are called hadrons. Okay. Example of mesons are like kaons, symbol is K, and charge is -1, is made up of S and U dash. Okay. I will come to that, what is strangeness, after some time. This is nothing but a strange particle. Why are some particles strange? Why are some particles called strange? Now the answer is lifetime for normal particle is 10 power minus 23 seconds. But these strange particles have lifespan of 10 power minus 10 seconds only. 10 seconds, because they behave differently. As they behave differently, hence they are called strange particles. Now I will come to something called the baryon number. All the quarks are given a baryon number of plus 1 by 3 and antiquark are given a baryon number of minus 1 by 3. So we have something called here now the conservation rules. Okay, we have something called conservation rules. So if you have an equation, for example, if somebody says that okay, pi, the proton plus pi minus becomes neutron plus pi naught. So we have to now verify. So how do we verify now? We are going to verify now. First we will verify from charge perspective. Charge. Proton 0. Sorry, not 0. Proton is plus 1 and pi minus is minus 1. Neutron is 0 and this is 0. So which means 0 equal to 0. So charge is conserved. Okay. Next we have to see lepton number. Proton is not a lepton, so 0. Pi already 0. Neutron is 0, 0. So conserved. Then we have to see baryon number. Proton has plus 1. Written as quarks are given a baryon number plus 1. So how do you know proton has plus 1? So let's say proton, we wrote it as it is made up of UUD, right? So it's like 1 by 3 plus 1 by 3 plus 1 by 3, 3 by 3 is equal to 1. So this becomes the baryon number. So 1. This is 0. Neutron is also 1. Same reason. Proton is 1, neutron is also 1. And this is 0. So again conserved. Then comes your strangeness. None of these particles are strange particles, so we can just say 0. So conserved. So you have to always use first these 3, 1, 2, 3, always 3. This a possible use, otherwise the 3 can support you. Okay. Hence we can now say that the above interaction is possible. So this is how we actually work on this. Is possible. Okay. Now we come to something another important, and that is the understanding of fundamental forces. Okay, there are 4 fundamental particles. Four fundamental particles. What are they? One is your gravitational force. And you should know that range is infinity. Then second is the weak nuclear force, and range is 10 power minus 18 meter. Third is electromagnetic force, range is same as a gravitation, infinity. And fourth is strong nuclear force, which is 10 power minus 15 range. Okay. Now, in nature, in nature, any interaction happens due to these exchange particles. So for gravitation it is gravitons. For weak nuclear, it is W plus, W minus, and Z0 bosons. Basically, bosons means your this quarks and leptons. It affects on these only mainly. Then comes your electromagnetic particle. For exchange is photons. Okay. For strong nuclear interaction, it is gluons. And mesons. These act on quarks, hadrons. To understand this further understanding Feynman diagram are used. The diagram has position in x-axis and time in y-axis. Let us say example, a proton becomes neutron. So we are having here time, we are having here position. So if I have to write the equation, a proton to become a neutron, I know what's going to happen here. I need 1 0, so it's a beta plus, and then I will get an antiparticle. Just one error. Yeah. The whole idea is, if this is an antiparticle, then this has to be a particle. So if I have to put this here, I go like this, and then I have two more. Now beta plus, the arrow is down, mu e, the arrow is up. Note, this is very important for us. You have to note particle direction is upward, okay, and antiparticle direction is downward, okay. So particle direction is upward and these are always downward. Now question is, what comes here now? I don't know this x, but I know one thing, that the proton will be equal to x plus n, and this is happening. If you go up little, you will see that I wrote here the weak interaction always happens in quarks and leptons. So here this is a weak interaction. So proton is +1, x, neutron is 0, which means x has +1 charge. Therefore, again if I go up little, and if I see here it is written W plus or W minus, so I will come back here and say that my x should be W plus. Okay, so this is how the questions work. Let's say we do another example. Let's say this time it is a neutron which becomes proton, and then you don't know x, but then you know it is like this, and this time you get electron and you get y, because your neutron 1 becomes proton, so becomes -1 beta 0, and this is a particle, okay. So I will get this, which is going to be a antiparticle. Now again same thing, so n, is equal to x plus p. N is 0, x and p is 1. So x is negative 1. So this is your charge. Therefore, my x is nothing but W minus. That is how you have to put here. Okay. So x is nothing but W minus. So I have to put here then W minus. The final part is that in a general case, leptons and quarks should have zero mass. But experiments have shown that these particles do have some mass. So, to understand this new theory, Higgs mechanism was used. They found some new particles and called them Higgs particle. So that is the end of particle physics in IBDP physics. So thank you.